To accomplish the project tiled convolution neural network, I have used two softwares, namely MATLAB and ModelSim. The convolution here is applied on a grayscale image named clock.tf. The image is read in MATLAB using this code. So this is read into the matrix called clock using the command imread, which is a built-in function to read the images. So this produces a clock named matrix, which is 256 cross 256, and each is an unsigned integer of 8-bit. So let's open to see how is it. So it is stored in a decimal format inside the matrix containing 256 cross 256 rows and columns. So I need to give this input to the ModelSim. So I need to convert that to a binary format using decimal to binary function, which is a built-in MATLAB function. I have converted that to a binary, each pixel value to a binary number with a precision of 8, and I have stored that in a text file where each line contains a pixel pixel value, which is 8 bits binary value. So here is the text file. As it is 256 cross 256 matrix, there will be 65,536 values. For the convolution, I am using floating point adder and multiplier. So I need to convert the numbers which are in the binary format into a floating point numbers. The floating point numbers contains 16 digits, the first one being the sign bit. As it is an unsigned number, the first digit is 0 and the remaining 5 bits are the exponent, and the mantissa is of 10 bits with an hidden 1. So this module takes the input 8-bit numbers and it converts to a scientific number depending upon the values of bits in the binary number. And then I have written a test bench which reads the data from the input file and produces a 16-bit output, which is the scientific floating point notation of the pixel values, and this is returned to a out.txt file. So let us see how it looks. So this is the out.txt file. So it's converting the pixel values into scientific floating values, and here is how it looks. Now we have set the input matrix in the required format. Now let's see how the convolution is to be done and what are its parameters. Given W1 is 256 and H1 is 256, which implies the width and the height of the input matrix is 256 and 256, and the depth is 1, which because it's an grayscale image, it has a depth of 1. Whenever you take a color image, it has a depth of 3, which implies the R, G, B values at each pixel. Now you have a filter to be 1, which indicates you would multiply the input matrix with 1 filter to get the output matrix, and you have the F, which is nothing but the spatial extent, to be 2. Let us see what does the spatial extent actually means. So let us take this, let us suppose that this 3 cross 3 matrix is a part of 256 cross 256 matrix. So whenever you say a spatial extent to be 2, at a time you would take this 2 by 2 matrix and you would multiply with the weights, which is also nothing but 2 cross 2 matrix, and by multiplying that you would get the first element in the output matrix, that is 0 times 0 is 0, 0 times 1 is 0, so 0 times 1 is again 0, and 2 times 1 is 2, so you would have a sum of 2. Okay, now let's see what are the other parameters. So you have a stride to be 1, so the stride actually represents. So whenever you take the first 2 by 2 cross 2 matrix, because it has a spatial extent of 2, and now you would leave one column and you would take the next 2 by 2 matrix, that is this matrix, this 2 by 2 matrix, to get the next element of the output. So we are leaving one column in here, which is nothing but the stride. So using these parameters and using the formula, you would obtain with the 256 cross 256 matrix, you would obtain an output matrix of width to be 255 and height to be 255 and depth is 1 again. In the project, there has been a condition that you can't use more than f units of 416 multipliers or adders. Here the f is given to be 2, so I can use at most 2 multipliers and 2 adders. So in order to use just 2, I have used a pipelining sort of technique, which processes which gives the first element of the output matrix after the end of 4 cycles, and it takes another 4 cycles to process the second element of the output matrix. Let's see the architecture. So I have been using 2 multipliers in here and 2 adders. So at the second stage I have a mux which has a control signal or the mux select signal to be 1, so that it would just add 0 to my intermediate value, and in the next cycle it would take the intermediate value and would add with the second row, the second intermediate value, so that it would give the output at the end of 4 cycles. So let's see the architecture. So I have taken A and B, W1 and W2. This A and B represents my first row of my input matrix and first row 2 elements of my input matrix, and these 2 indicates the first row of my weight matrix. So I'm multiplying A and W1 and I'm storing the result at the end of first clock cycle into the registers. Now I am adding these 2 values, means I have done 2 multiplications and I am doing the addition in here. And in the next cycle I have been selecting the mux select to be 0. So I have the intermediate value and I have been adding a 0 to this, which doesn't change anything because I'm adding a 0. So it gives A times W1 plus B times W2 at the end of third cycle into the output. Parallelly, the second input, the second row of the second row first 2 elements and the second row of the weight matrix is fed into the first stage. So when the first value is being done, being added in here, it's being multiplied in here. So and in the next cycle I would select the mux select to be 0, so that it would use the intermediate value as one of the input to the second adder. So as a result I am getting the output at the end of 4 cycles, which is nothing but the first element of the output matrix. So I have used a test bench which produces a clock in here, and I have given the delays of the mux, and I have the input values which are we created to be the pixel values in the form of float values, that is nothing but the float input, and I have the input weights, and I'm feeding the input vectors in here. With certain delay I'm feeding the next input vectors. I have used the offset of 255 and 256 because in models in Verilog it starts with the element 0, right? So I have 0 to 255 values in the first row, and in the second row I would have 256 fifth value. So whenever you start with a 0 it would be 255, so I should take the element first element of the first row, second element of the first row, and then the third element has to be the first element in the second row. That's how I have fit into my architecture using delays, and these are the weights I would take, and I have created an output file so that the values generated in here is fed to the output.txt. So let's run this to see how it is simulated. So I'm running my final test bench in here. So I'm adding all the values to the, so it is taking 3264 nanoseconds to completely do all the computations of 256 cross 256 matrix. So I'm running it. It may take quite time because it's 3264 nanoseconds. This is my end results. It looks messy in here, so let's open the output.txt file to see the output. Actually, we expected a 255 cross 255 matrix, which is to be the result according to the formula in here, but we have some extra computations, and so let's see what are those and why did we incur some extra computations. So in here we'll just see how I incremented my final test bench inputs. So I have incremented vector inputs to be vector inputs plus 1, which is that it is incrementing each vector by 1. So when you are incrementing by 1, there is a case which you don't want and which is in the output. So let's see what is it. As we are incrementing by 1, first it is taking these two values, I mean this input matrix, and in the second case it is taking these two values, and in the third case it's taking these two as one of the column and these two as one of the column, which is an unnecessary computation. So what I did is I just put this output.txt into the matlab. So here is my the code I have written for the final matrix. So I have put that output.txt into the matlab, and I have reshaped it so that I can delete the last column, which is my unnecessary computation, and I have rearranged it to form again a 255 cross 255 matrix. And let's see how this final output looks now. So this is my 255 cross 255 matrix, which would incur or result in 65,025 values. Coming to synthesis and power estimation calculations, I have added these code into the test bench so that it would create me a VCD file which is used for the power calculations. So this would create me a cnn.vcd file, and using VCD to CIF conversion, the statement in the terminal, I have created my SAIF file. So let's see what I have done after that. So I have used WinSCP, which is a drag and drop tool, to pull all these verilog files into the server. So I have put all those files in here, that is my all the module files, all the verilog files in the VCD, and using the sentence shown, using this kind of code, I have created a SAIF file, and now I will do the synthesis. So first I'm in the scripts directory, I have modified the synth.tk file accordingly. So I have added all the verilog files in here, and next I have added my SAF file and created the instance name for my DUT, and I have this is a sequential program, so I have a clock in here. So I said what is my clock pin in here, and I put the loading accordingly. So it is driven by it's driven by a flip-flop at the end, and so all this would create me the reports, the timing reports, and in the report directory. So let's see what it does after the synthesis. So in order to do the synthesis, I have opened a terminal and I have used EDA-tools, which sets all the required tools, and then I have run the script using the DC shell command. So this is running my synth.tcl, and it is optimizing all the things, so it may take quite time. Now I have entered makeall, which is the command, so that it will produce all the reports into the synth.out. So let's have a look at how my reports are. So I have my top module is CNN, so I have all that named under CNN. So this is my timing report. So this is how my Slack looks, and this, let's see the power report. So it's taking a total of 122.5 millivolts. That is my dynamic power, and this is my leakage power. And now let's see what's the area it has taken in the area report under here. So this is the area it has taken. So this is the area. That's what I have done for my project. Thank you.